Hello and welcome to another video in the series of RF circuit design using Quicks. In the last couple of videos, we saw how to set up S parameter simulation and how to define various transmission lines such as an ideal transmission line and a microstrip line. We also saw how to do a sub-circuit simulation in which we have a top level block and inside we have some circuit implementation. In this video, we will look at impedance matching using quarter wave transformer and something called as parameter sweep. So let's go and create a new project. I'll name it as QWT and this is my project 5. It's done. Let's save the schematic. QWT underscore project. It's saved. So you know what quarter wave transformer is. Quarter wave transformer is a section of transmission line which is quarter wavelength at the frequency where you want to do matching, and it helps us transform the real impedance, real load impedance to match with the source impedance. So as I said, it's a quarter wave transmission line, and in this case I'm going to take microstrip line here. I'll place it here, and we need to define the substrate for it. So let's go back. If you haven't watched my previous video, you can watch it to understand what we are doing here, why do we need a substrate, and what the different parameters mean. So we have defined the substrate. Let me name it also as FR4, and here also we need to make the changes. FR4 apply, okay. And so I have a transmission line here. Now I'll just keep it for like that, and I'll go to lumped components and I'll place a resistor. So suppose this is our load resistor, so I'll call it as RL, apply, okay, and my load resistor is 100 ohms, and I already have a source which could be your VNA port, and it will be always at 50 ohms. So you see, what we want to do is we want to connect the source with the load, but we want to do the matching because we want, let's say, the power to be transferred to the load, or we want to achieve matching. So for that, there are a couple of techniques, but the simplest one is by using a quarter wave transformer. And as I said, that a quarter wave transformer is nothing but a quarter wavelength section of a transmission line of it could be anything. For my case, it's microstrip line, quarter wavelength, and that quarter wavelength should be at your frequency where you want to do matching. And the formula for this impedance transformation is given by root over of Zn times Zl. So Zl is our RL and Zn is the input impedance. Input impedance from this part, from by looking into the this network from the source side. So Zn, I want it has to be 50, which means that the impedance of when I connect this and this should be 50. So that if this is 50, then my this port 1 or power source is going to be matched with 50 ohms. So Zn is 50. So if I do root over of 50 times 100, which is my Zl or RL, the impedance that we get is around 70.7 ohms. And let's see how to get 70.7. Then we need to again use the tool. We need to go to line calculation, and this time we want 70.7 ohm. Okay, I had already put it here, but let's just, for sake of this, 70.7. And this time we also need to put the angle, because the angle is the basically the electrical length, and for quarter wavelength, angle will be 90 degree. You can do the calculation. Beta L is equals to 90, so it should be 90, and then you can find out like the quarter wave. You can put length as lambda by 4, and you can do the calculation. So for that we need angle to be 90 degree for a quarter wavelength, and the impedance as we calculated from root over Zn times Zl is 70.7 ohms. And all these values looks good to me. And the frequency, this is important now. Let's say I want to match it at 4 gigahertz, so I'll just keep it like that, and then click on synthesize, and we have these values. So W is 1.6, L is 10.5. We need to use these values here. So I'll put 1.6 and 10.5. 1.6 and 10.5. So this is going to give me an impedance of 70.7 ohms on this value, and this length of 10.5 is going to be a quarter wavelength at 4 gigahertz. Let's go ahead and verify that. We can always verify that by simulating. So I make the system, I connected everything. Just drag it so that it's in the level, and let's define our S parameter simulation. This time I'll do it for 10 gigahertz, and I'll increase the points. So let's run it for the entire 10 gigahertz. Before that, we should also convert dbs11. Okay, so we are good to go. And in this case, if there, because we have only one power source, we will have only one parameter, which is S11. Let's run the simulation. No error so far, and let's see if what we get. So we have a good looking graph here, and we already see that we have a nice curve here. Let me again change the limits in steps of 1 gigahertz. Okay, and you see we have a nice dip here at 4 gigahertz, uh, which shows that okay, the lowest return loss, or the lowest reflection, is at this frequency. And we can verify if we are at 50 for that frequency by looking at the Smith chart. We see a nice circle, and we see it's pretty close to 50, maybe not exactly 50, because there are a couple of numbers here and I just ignored them, but we should be pretty close to 50, as you can already see here. You can move it using your arrow keys, and yeah, I think this is the lowest one where the reactance is also lowest, and we have an impedance of around 51.2 ohms. Maybe just to play around, we can go and 1.67, 10.56, and 1.679, and we can, maybe we'll see something change. Yeah, it's changed now, so it actually became a little worse, but okay. So but we see that it's okay, it's pretty close to 50. There's some error margin, and we may have to like change certain things here to get to the proper 50 ohm. One method is like you can go to this line calculation, and we can like again do the calculation. You can put these numbers here and try to tune it, but there's another method that can be done, is we can use something called as parameter sweep. It's available under the simulations option, and we can go for parameter sweep. In this parameter sweep option, we have so what parameter sweep does, as the name suggests, it sweeps a given parameter, which means it's going to sweep some variable within the limits that you put here. So let's see what all options do we have in parameter sweep. If I double click, it asks what kind of simulation we want to run whenever a parameter is changed. So it's SP1, which is parameter simulation, because we have only one type of simulation here. And the sweep parameter, currently it's R1, but I don't want it to be R1. I want it to be something of the microstrip line. So width, I'll keep it like that. I won't change the width, which let it be at 1.6, because it's pretty close to 50 ohms. But maybe I'll change the length. So I'll call this as length QWT, length of quarter wave transformer. The sweep type is linear. I want to switch between the points in linear fashion, and obviously it cannot be in ohms, so because it is length, so it has to be in mm. We'll define something close to this. So this is at 10.56, so I'll start at 10.5 mm, and I'll go till 11.5 mm in steps of 0.1 mm. So we will have around 10 curves. Apply. Okay. But we also need to define this parameter here because currently the length of this microstrip line is fixed at 10.56. So let's go ahead and put here the sweep variable which we want to sweep, which is LQWT. And now it will automatically, this LQWT will automatically take these values and put it here, and we'll get a simulation. Let's go ahead and run the simulation and we'll see. As you can see, we have around 10 curves here for different values of lengths. For example, this is for 10.5 mm, and you can again select the marker and you can use up and down arrow keys to switch between different curves. So I am here, and let's just move. Let's see which is at 4. This curve is at 4 gigahertz. Yeah, this is at 4 gigahertz, which is like 10.5, which we received from previous one as well. And now you can see, you can understand when I change the length of the quarter wave transformer, how the matching point is moving. And you can check the same here, but since the impedance of the line is same, all the curves are basically on the same, they are basically tracing the same point. I can show by changing the different curves. So if you use up and down arrow keys, you can see the LQWT is changing, which means that it's moving to different lengths of this transmission line. This is good to, this parameter sweep is helpful when you are doing such kind of simulations where you want to sweep some parameter or tune something and check how my results are going to, vary. It's also helpful while you're doing, let's say, power amplifier simulations where you want to sweep the input power to the amplifier to find the saturation point or PVDV, etc. Let's go and maybe change the width of this time. Now I'll set it this thing as 10.5 mm, and I'll define this thing as W of Q WT. I'll go here, I'll change W of QWT here, apply, and this time I'll change this here. I forgot what our width was. It was 1.6. So I'll sweep starting somewhere below 1.6, 1 mm to 2 mm, and I'll put it such that it covers 1.6 value somewhere here. So I'll have 6 curves this time for WQWT, but this time L is fixed. So we can go ahead and run the simulation again, and you see how we have different fashion of the curves here. Now, since in this case I am changing the width, which means it's changing the impedance, and by changing the impedance I have a poor matching, which we can see from here as well. It's better to see on the Smith chart. So currently for 2 mm, and this is for 1.8, this is 1.6, and we see for 1.6 we are closest to the 50 ohm point here in the center, which again shows we can also check here for the same value of WQWT as 1.6. Yeah, so it's 1.6 mm, and you can see at 1.6 mm, because we are closest to the 50 ohm point, we have a much better return loss. So in this video we saw what is quarter wave transformer, how to do quarter wave transformer matching. I forgot to mention one thing, that quarter wave transformer matching is good only for a narrow band matching, and it's good only for real values of impedance. It won't work if we have a complex load. That is the limitation of the quarter wave transformer, but that is already there in the microwave theory. You can go through the text. I just wanted to show how to simulate how you can do a quarter wave transformer impedance matching in Qwix, and the parameter sweep option, which can come quite handy when we move on to some advanced circuit design. So that's it for this video. Thanks for watching.